Hello, everybody. This is Claes Strannegård, and today I'm going to talk about the ecosystem path to AGI. And this is joint work with several people from our university, Chalmers in Gothenburg. So first of all, why would it be interesting to model ecosystems? Well, there are several reasons. One is to understand ecology, population dynamics. And here we have a very early example, the so-called Lotka-Volterra equations. Two differential equations that talk about the number of rabbits and wolves, for example, predator and prey. And then they show this oscillating pattern that can also roughly be observed in nature. Here's a much more recent example from Google DeepMind and Peter Sunehag and colleagues. They've been developing a reinforcement learning model with predators, prey, and apex predators. And in that ecosystem, they show that collaboration emerges among the predators, for example. Here's another one, understanding economics. That's another reason for studying ecosystem models. And this is work by the AI economists. And they can make reinforcement learning simulations and study questions such as which tax system is best given certain goals. That's also kind of ecosystem involving people. And still another reason, to support sustainable decision-making. For example, when determining fishing quota, one may use models that are similar to the Lotka-Volterra equations, differential equations or difference equations. And they also use a map, so there's a spatial representation, and then they can run simulations and predict the effects of fishing at certain levels, and thus it can be used for determining recommended levels for fishing. Another application is to make video games, as in this example from this year, a game called Ecosystem, where you build your own creatures and watch them evolve. Okay, so those were a few reasons, and I'd like to add another one, which is to try and model the emergence of natural intelligence. So natural intelligence is the result of an evolutionary process, as we all know. And that process took place in an ecosystem, of course, a big one, the Earth. So that's where real intelligence actually emerged. So then, isn't it natural to look there for inspiration when it comes to AI and AGI in particular? So in nature, there's always a selection pressure on all organisms concerning their ability to survive and reproduce. Challenges of all kinds all the time. And part of that selection pressure targets the body, and other parts target the adaptive behavior, or both. And as I see it, at least, intelligence is just a part of adaptive behavior. So part of that selection pressure is also aimed at intelligence. However we want to define it, really, doesn't matter. Okay, so then the title of the talk, the ecosystem path to AGI. The idea there is to develop a large-scale ecosystem simulator that emphasizes animal cognition. And one thing that we think is really important is not to forget any of the two really big forces of adaptation. Maybe there are more too, but at least those two shouldn't be left out. And I'm thinking about evolution and reinforcement learning, or learning in general. And there are lots and lots of ecosystem models, but many of them, most of them, by a big margin, leave out one or more of those two huge forces that are present in nature everywhere, more or less. Okay, so another part of this idea is to use a generic model of animal cognition. And that means that one instance of the model could be a fly, another could be a shrimp, a third could be a bird, etc. And then we just want to start the simulator with a certain ecosystem and then let it run, and not to interfere at all. Because the ecosystem itself will create all the problems, all the training data, if you like, and keep improving. So things will happen even without any human interference at all. And what we aim to do is to exploit this automatic selection pressure that exists on intelligence. So it looks a little bit like this. We can imagine an aquarium with fish and other species. And lots of things are going on there, even if we don't interfere at all. So the fish maybe learn to collaborate, or and they learn to compete, and there's always this arms race going on as soon as there are predators involved and prey. So animals that are sufficiently good at these challenges will be able to reproduce, but the others won't. So there will always be a motion towards more adaptation, and in particular, behavioral adaptation, and in particular, intelligence. That's the basic idea. So in ecosystems, and in this aquarium in particular, there is a built-in selection pressure on intelligence. And we are suggesting to use that selection pressure and try to produce artificial intelligence in a similar manner. Okay, here is a quote by David Silver and Rich Sutton and other people about reinforcement learning. And they are suggesting that powerful reinforcement learning agents could constitute a solution to artificial general intelligence. So some people think that reinforcement learning alone can be enough to produce AGI. The approach that we take here is more liberal, because we also emphasize evolution. And as we will see later in an experiment, there are some indications that evolution plus reinforcement learning is stronger than reinforcement learning alone. Okay, so when we looked at what kind of ecosystem simulators there are, we saw that many of them are quite limited. So if the ambition is to reproduce real animal behavior, then the simulators have to be much more sophisticated in many cases. So we made a wish list that contains these things. And then we tried to develop a simulator that would meet all these requirements. So for example, we have to have reproduction, like both sexual and asexual reproduction, so basic mechanisms. Sexual reproduction based on physical encounters, not least. Not the classic idea of just selecting two individuals from the outside and crossing their genes and so on. We like to have generic models of organisms in general, and death criteria, generic model of the nervous system that can be instantiated in different ways. And we want to add more than that. We want to add reflexes as well, which virtually all animals have. And yeah, individual and lifelong learning. And we also want the animals to live in a realistic terrain. So we want to import real terrain data and let that be the terrain. Okay, so I will present our simulator that we built called Ecotwin. So it's supposed to be like a digital twin of a real ecosystem. That's the goal. And it's an open source software, which is based on the game engine Unity. And that gives a lot of advantages, shortcuts. And we aim for all the properties on that list that we saw a while ago. There is a prototype that's accessible on GitLab. And we have a website also for this simulator. And what you see there is a screenshot with, I think it's a wolf hunting a deer, hard to see in the middle there. All right, so now let me tell you a little bit about what this model looks like inside. And then the most important part, and the part that we are emphasizing in this model, is the cognitive model of animal cognition. And part of that, the big part of that, is the nervous system. So let's just look at some real nervous systems first for inspiration. And one thing that is quite striking is that real nervous systems are often not at all monolithic. They have separate units that are not necessarily connected even. And this is in contrast to, let's say, big deep networks and so on. So we wanted to follow, well, we were a little bit inspired by that. So first of all, we have reflexes. For example, positive reflexes like the knee reflex. And we also have negative reflexes that prevent us from doing things, such as the diving reflex, prevent us from breathing in water. Then we have the basal ganglia, and they map sensory signals to actions. We have the insulae, which map internal signals such as our blood sugar level and also smells and things like that, pheromone smells maybe, and link them to the reward system. And we also have the medial prefrontal cortex, which predicts the outcomes of actions. So those are our four sources of inspiration mainly. And this is how we model it. We have a set of sensors and actions. And then we have a reflex network which takes nodes as inputs, sensors as inputs and outputs actions. And that one is not being trained, just like our knee reflex, for example. It's not trained and it can also not be untrained, I think. Then we have a policy network, which takes sensors and actions. No, sorry, it takes sensors and then outputs actions, of course. And that one we train with reinforcement learning, as usual, policy network. Then we have this happiness network, whose job it is to compute the reward signal. And that one is also not trained. And it's a network or a function which takes in sensory data, including interoceptors for blood sugar and so on, and then output a single value that summarizes the happiness of the animal. And then we have a prediction network with inputs, nodes, sensors and actions, and outputs sensor nodes. This is to predict the next scene. And this is what's being used in model-based reinforcement learning. Okay, so how do we go from happiness to reward? It's very easy. It's written there in yellow. We just say that the reward is the difference in happiness from one time to the next. And that's, yeah, if you wonder, it's actually equal to training directly on happiness, but this is more in line with ordinary language use to regard it as the difference between, regard a reward as an increase in happiness and a punishment as a decrease in happiness. All right, so here we have an example of a happiness network. And it has 3 inputs: glucose level, water level, so this is the body water level, and sheep smell and wolf smell. And then those 4 inputs are summarized, computed into, translated into a happiness signal. And if we look at the roles that the different inputs play, like the glucose, for example, if it's low, that signals hunger. If the water level is low, it signals thirst. And these inputs might also lead to social behavior. If there is a sheep smell, for example, for this little lamb, then it will perhaps move towards sheep smell, feel happier if it has more sheep smell, and feel less happy if it smells wolves instead. So that will have a negative effect on the happiness. But these 4 signals might be compiled into one scalar value, which represents happiness. Okay, so I'll show you a concrete example of a happiness function. Let's say happiness function now instead of happiness network, but as we all know, it's not hard to convert a happiness function such as this one into a neural network by supervised learning. So here we have the happiness depending on 2 variables, water and energy, just like we saw before, or glucose and water maybe. And we can see that there is a sweet spot there when the happiness is at the max. And that happens when the water level is not too much and not too little, and the energy level is also not too much and not too little. Maybe it could have a different happiness function. Maybe it could be the more, the better of everything, then the happiness function would look different. So here is another example for the lamb. Maybe it has, we're only looking at the temperature and smell in this case. I just want to be able to visualize it. Here we might have a happiness function such as this one. So you see that if the temperature is too low or too high, then it will go down. The happiness will be 0, which can almost be like it's the worst possible. It could mean that it's dead in principle. But the happiness also depends on sheep smell because it's a social creature. And as you can see, it gets happier when the sheep smell is bigger. So it likes to be around other sheep and have a medium temperature. That's what makes it happy. Okay, so now let me show you. So this was just a brief description of the most important part of the model, which is the nervous system. And we looked now at the happiness function in particular, happiness network. So what can we use this model for? Is it any good for simulating aspects of real ecosystems? Can we reproduce animal behavior in some typical situations, or what? So here is our first study. It's about the Lotka-Volterra dynamics that we saw before, but in this case, we have 3 species instead. We have grass, and then deer that eat the grass, and wolves that eat the deer. And then we run our simulations, and we get, after training, we get a pattern like this. So here you see the characteristic behavior that first the grass goes up, and then when there is a lot of grass around, the deer will increase, the deer population will increase. And when the deer population increases, conditions are good for the wolves, so then they will increase. But when the wolves have increased, then there are many wolves, then there will be fewer deer, and then less to eat for the wolves, so they will decline, and then the grass will be able to, the deer will be lower, and the wolves will be lower, so then the grass will grow and the whole thing will start again. Okay, so we got this, exactly this kind of behavior that we can also see as solutions to the systems of 3 differential equations in this case. So yeah, and a completely different little ecosystem here. It's about plankton in the ocean, and there are phytoplankton that are near the sun on the surface because they depend on photosynthesis. And we have copepods that feed on phytoplankton. And then we have krills that feed on copepods. And the copepods in nature, they have developed a behavior which is called Diel vertical migration. So they go up at night to feed on the phytoplankton that is near the surface. And then they go down again, go deeper in the daytime, because then it's darker down there, and it means that they will be less exposed to predators that have eyes. So this thing happens in the oceans all the time, and it's a huge migration, vertical migration that goes on every day. All right, and then a third study that we did was about reflexes. Some people might say, well, there's no need for reflexes because reinforcement learning can take care of that. And we made a study that was designed to test that hypothesis or to overturn it. So we looked at 3 different types of goats. So there's grass and the 3 different types of goats. So they have different genes, and they have, let's see. First of all, there are 3 types of food that we call good food, bad food, and very bad food. The very bad food is deadly even. The good food brings reward, brings energy. The bad food maybe makes the goat vomit or something. So it takes away energy, it's like a punishment. And the third type is deadly. So the goat is gone after it tries a piece of food of that kind. Right, and then the thing is that with reinforcement learning, there's always a certain amount of exploration. And at some point, the goat might explore tasting this deadly thing. And then it dies, of course. So there is no way that it can learn it. Then we have to use things like resurrection and like they do in reinforcement learning, which is not exactly natural. So we think that there are good reasons for reflexes, why almost all animals actually have reflexes side by side with reinforcement learning. And this experiment, well, I don't know, supports that to a certain extent. So as you see here on the curves, the goats that take over the population are the red ones, and they are the ones that actually have this reflex, which prevents them from eating poison or deadly food. So the other ones, including the pure reinforcement agents, they are being less, their fitness is lower in this case. So this is why animals that get a mutation which will prevent them from eating certain foods that are deadly will dominate in the population eventually. So we conclude here from that reinforcement learning and evolution is a more powerful combination than reinforcement learning only. So yeah, thinking back on that quote again from David Silver and Rich Sutton, where they said that reinforcement learning alone can probably produce AGI. Yeah, it looks like it's more efficient, at least in this case, to have both reinforcement learning and evolution. Leads to more powerful agents. Okay, so just a few words about our next step. We plan it is to look at real ecosystems. So we want to read data from real terrain data and put that in our 3D models from Unity. And then we want to populate it with animals. And the animals come with brains, so they are like pre-trained. We have pre-trained foxes and rabbits and wolves and deer and goats and so on. So we want to keep on doing that. And that can be, yeah, among other things, it can be useful for analyzing the consequences of human interventions in ecosystems. For example, what if we build a highway in that terrain, which is incidentally from Grand Canyon? What about if we allow hunting there and so on? How will that affect the ecosystem? Which subpopulations might go extinct and so on, local populations. So that can be a help for anyone who's trying to make sustainable decisions. Okay, so to summarize, we discussed this bottom-up approach to AGI. First, we can model simple ecosystems with simple animals, try to reproduce animal behavior, including adaptive behavior. And then we can add complexity to the ecosystems and see how much we can do. Then we introduced this model Ecotwin and its nervous system model, which includes a reflex network and a happiness network. And we looked at some simple ecosystems involving predator-prey, for example, and the plankton with a vertical migration. And we were able to obtain realistic behavior. Realistic behavior emerged. We never programmed the krill, not the copper poach, to go up and down, for example. It's a behavior that emerged in that system. And yeah, so that's what we did. Obtain some realistic behaviors in some very simple ecosystems. And yeah, we think that this path could be promising because it's actually the path that nature took. So why not try to model it a bit more ambitiously? So thank you very much. And you're very welcome to contact me if you want to talk more about this or join our project. Thanks a lot. Bye-bye.